All right. Hello and welcome everyone in Agoda and our external guests to Agoda Tech Talks. Today we will get to learn about Agoda's in-house log aggregation platform, Log Kestrel. Eugene here will guide us on how we can efficiently handle the management of massive amounts of logs each day. I believe some of you may have heard about this before because Eugene has conducted a workshop last month on this topic. So please note that the content of this event will be quite similar to that one, but we also think that this could be a good opportunity to extend the reach of our discussions to everyone here in tech and also to wider audience that joined us today. So we hope you get to learn a lot of things. If you have any questions along the way, please feel free to send in the chat box or wait until the end of the presentation where we will have a Q&A. Okay, so without further ado, please join me in welcoming Eugene.
Hi, everyone. Hope you have an amazing day. Hopefully this meeting will be interesting for you. Right, let's start then. So first of all, who am I? My name is Evgeniy Zuykin. I am a technical lead in Agoda, working on observability platform. Basically, observability means everything starting from logs and metrics and something more, for example, anomaly detection. Today, we are going to talk about logs. And again, guys, please bear with me to the end. If you have any questions, we will have a separate Q&A sessions. So we will have enough time, hopefully for everyone, to answer your question, but we will not have a question in the middle of the talk. Thank you for understanding. So let's start with simple things. Basically, what is logging? Hopefully everybody knows that. Logs are just like a text representation of any kind of events which developers wanted to have later analyzable, usually written to either std out or on disk. So, but why do we need a log aggregation? Basically, if you have just one simple server or your application is deployed on small number of services, you can just go to the services directly, or if you're using clouds, you can just open the console from one specific pod and you can open and you can see what are the logs from this application from this particular instance. But for example, if you are deployed in a large scale, for example, of the scale of Agoda, it will be quite problematic for you to get exactly the logs from, let's say, thousands of different instances of applications. So that's exactly why and which problem does log aggregation platform solves. It provides you centralized logs access, meaning you can tell, I want my logs from application X for last 15 minutes. And I want to see what the logs, for example, for error did it have. So this is the first use case. Second use case, sometimes you just want to know how many logs did you have. For example, how many errors did you have? This is quite important because having errors meaning something is wrong with your system. So you usually want to monitor that. Or sometimes you even want to have some log patterns or like something else. And you want to have a monitoring over that and you want to have alerting over that. That is another thing which log aggregation is solving. So Log Kestrel. Basically, Log Kestrel is Agoda's in-house log aggregation platform. It's written in Rust, and it's entirely inspired by Grafana Loki. Yeah, basically what we are going to talk about today, we will cover briefly the overall architecture, and we will go into each separate components and we will discuss how do we store the data, how do we ingest the data, what indexes do we use, which formats do we use on the storage, how do we transfer the data between different components of the system or the network, and some other interesting things. But first, I would rather start with functional requirements of this log aggregation platform. Basically, we wanted to have a platform which would provide people fluent real-time log access, meaning you just want to see something which happened on production like less than a minute ago, obviously, but as fast as possible. So you wouldn't need to go to the servers, but you want to have as like your data accessible as soon as possible. Another thing, obviously, you want to have the sourcing for alerts and dashboards. Like as we discussed, you want to have graphs, like these fancy things which are hanging on the monitors throughout your rooms, on the floors. Other things, like if you're doing something interesting, for example, you're querying the data for last couple of weeks, let's say, and you want to get some, for example, how many particular events did you have throughout last some time. But another thing which we wanted to have, which we've seen in Grafana Loki, is real-time data post-processing, meaning if you have some logs, we want to do some additional filtration. We want to do some additional, for example, I see the URL and I want to parse particular user or like parameter from the URL, and I want to group by this this parameter which I've seen. So I would see how many particular occurrences of such variable I see in logs. So these are the functional requirements and our hardware requirements. Let's start with the most controversial one, which is 10 RPS. Doesn't sound that much, almost everyone having more. But if you will actually have a look what exactly the request for the system is, it might shock you because this request might require traversing tens of gigabytes for each one, 10 gigabytes of data, just to get your response. For example, if you want to calculate number of logs, or if you want to post-process and calculate, it might be really challenging. Another thing, we have about 150,000 of logs per second coming in different regions. And since we talked about regions, we also want to not overload our network by constantly replicating the stuff between the regions. So we want to also have the cross-DC federation. And a bit more about our scale. In day, we have about 100 of terabytes of logs. And the most important one, we don't want our users to be able to get their coffee until they will be able to get their responses. So another hard requirement, our P99 of the system overall should be less or equal to 5 seconds. So before going forward, I should tell as well what we are currently in the company using Elasticsearch with Kibana, and we are replacing it with the Log Kestrel, and we almost done so. So you can say it's almost a success story as well. So how the logs are going, basically you have a server or like pod, depends on where you deploy it. You have a log agent, which is getting the data from the servers, and it sends to Kafka as our main source. We've chosen Kafka for different reasons. The main reason is you can really operate with Kafka as a persistent storage for some time, for example, for a day or for 2, depends on your retention. And if you lose your data for the recent amount of time, you can just read the Kafka. So that's why the Log Kestrel has no other mechanisms for ingestion apart from just ingesting it from Kafka. Now about the architecture of the Log Kestrel as is. So we have here a lot of errors. So let me just cover all of them separately. So about the data pipeline, how do we ingest? Basically, we ingest everything from Kafka, and we have a core component of the system, which is ingesting the data and storing it further and serving some requests, which is real time. After that, after the real time saved the metadata in our relational database, and it saved the actual data in our blob storage. After that, we have historical API, which is serving the data for everything but older than 24 hours. And you have Federated API, which is basically deciding where to go for this specific request, either to federated, either to historical, either to real-time, either to both. Also, you have auxiliary thing, which called rollup, which is in charge of different things like retention and also post-processing if you want to give some some additional permissions to somebody and things like that. So yeah, basically these are the main components. Now let's go over each one of them. And let's start with real time. As I said, real time ingests the messages from Kafka. Also, it stores the queries for the most recent data because it's called real time. And it stores the last 24 hours of data on disk. Before we can proceed to actually the real time and how it does everything and yada yada, we should first start with what our start talking with what our log message is. So log message is looking something like that. So it has a lot of different fields. It has timestamp, for example, log level, I don't know, version, and a lot of different things related to different applications having the same logs, but we will have this one as example. So after the timestamp, obviously, which identifies specific log and when did it occur, we have application name, which is the primary key in our time series database, in our log storage. We use application name as a tenant identifier as well. For example, we can do a lot of different things. We can set up indexes separately. We can set up a quota separately, rate limits, and a lot of different interesting things. That's why we actually have something which our system usually don't have, or rather don't impose people to have. So we have primary key. After that, we're also mimicking the time series database here. So we have additional general index for all logs, which is basically like has tags which are limited, which are having limited cardinality. Cardinality, for those who are not familiar with, is just a number of unique values. And these are the things which are general for everybody in the system. So everybody having log level, everybody having server, cluster, and things like a logger name and exception type. After that, we have the actual messages. So we have them split it into 3 different things because people usually want to query them separately, which are message, exception message, and a stack trace. And each one of them can be very big. And we can query each one of them separately on UI as well. Also, we have separate secondary indexes, which are set up on demand. For example, some people want to trace their stuff, talking about tracing as well. So you can, if you know what, you have a lot of different unique values and you want to make your index much faster, you can ask and tell like, guys, I need an additional index, and we will create this index, and it doesn't have a cardinality limitation. So regardless of how many unique values you have, you can have you can have this index. After that, you can just label your data in a manner like you can put as many tags as you want, and basically no limitation on the rest of the data. It's just something you want to put into your data, and you still will be able to search by it, but the search will be quite slow. So we have this log message, and we will transform it into our data model. Data model called like log entry. It has series ID, timestamp, message, and not index tags. So to get this model, we are doing interning tags, and we are creating the series. So what does string interning mean? Basically, since we know what cardinality of main tags is limited, we can replace strings with integers. String interner is also can be named as dictionary creation. What does it mean? It means what instead of operating with strings, we can operate with integers. And operating with integers is much easier because they have much less memory footprint, and integers are basically just for byteware, non-essential. So you can do much more things with integers than you can do with strings. Not going to dive into the implementation, we'll just say what is non-resizable, highly concurrent, open address hash map, and that's it. You can read more in our Agoda tech blog. About our index. Index is effectively just a map of nested maps with the primary key of application name. And the tags, when I say tag, it's just a concatenation of all tags which you have for specific log entry. And the series is basically, imagine you have 8 different tags, and for each combination of these unique tags creates you the additional series. Since we know what our series count is less than 500,000, we can use brute force approach, just iterate over for specific application name, iterate over series, and it will be enough. This is exactly the case where brute force is enough. Smarter is not always better. So after we figured out the basics, we can now talk about actual real-time architecture. So we have Kafka, we have some in-memory components and on-disk components. Let's start with in-memory components. And as one of the first ones, we have ingesters. And ingester is just an entity which reads data from Kafka. And we have we start one ingester per one partition. Basically, ingester means a thread. And each ingester reads each separate partition from Kafka. For those who are not familiar, partition is just a unit of basically in Kafka you have several topics, and your data is partitioned. Doesn't sound good enough. Partitioned in the partitions of data. So what ingester is doing? First of all, it obtains the message from Kafka, parses the message. It doesn't matter if it is a protobuf or if it is the open telemetry, if it is a JSON or if it is the OTLP protobuf. You get it. You get some result out of it. You intern the tags, create the series, and then you submit your log entry to aggregation buffer. We will cover it in a bit. So after you ingester, so for your ingester to operate, you need metadata because you need to get index ID and like series ID and intern strings. That's where we have the metadata, which we have one metadata block per 1 hour. We have 24 blocks of such data in memory. Only first 2 blocks are mutable, and the mutable blocks aren't accepting new messages. So it's a bit tough to swallow, and a lot of questions are arising. First of all, why exactly 24 hours? We have a simple explanation to that. Basically, 85% of the queries are for last day. And we decided to store such hot data nearby because we have a lot of use cases for such hot data. For example, investigation of production issues which are happening right now, meaning like you don't need to go to to separate storage. You don't want to fetch your logs from there. You just store it somewhere nearby, and your access to them will be super fast. Another question which is arising: why do we need this mutability, and why only 2 blocks are mutable? So reasoning behind it, we observed what 95% of logs are sent in last hour, because usually your logs are posted now, like it always posted now, meaning your logs should be like always have recent timestamp. So 95% of the data is arriving at last hour. But because we are not living in the ideal world, sometimes the machine is lagging, sometimes we have network issues, sometimes log collector is just having too much stuff, and we are accepting the lag up to 2 hours, because like 99.99 of messages are being received in last 2 hours. Basically, the 5% or like a bit less than 5% are being received in this second hour. So why the mutability at all? In short, it's much easier to operate with immutable data. If you know your data is not changing, you can just easily cache your stuff, and you're solving one of the hardest problems in the computer science right away. And also, no need to worry about the graceful shutdown. Graceful shutdown of stateful applications, in my opinion, it's the last unnamed or either unknown problem in computer science. So if you want to mitigate the impact of your stateful application dying and not being able to recover, it's a big plus. Now, we covered metadata blocks and ingester. Now let's talk about aggregation buffer and why do we need it. Before it, we need to learn a new term called chunk. And in short, if you try to, you're obviously not going to store your logs fully in memory because you have hundreds of terabytes of them per day. It will be just impractical. So you're definitely going to write them on disk. And if you're writing them on disk, writing each message on disk separately is super slow. So we group them in memory and we store them in, like, we just call the batch of logs in chunks. And chunks are being grouped by hourly block, application, which is the primary key, and the log level. So in result, it looks like that. And another thing which I should mention is, since we have a lot of different instances of your application running anywhere, nobody guarantees what your clock are exactly aligned and what your messages in Kafka will be exactly ordered. So this is another problem. Why do we need chunks? When you write chunk, you receive them unordered. And after you write in this chunk on disk, you can exactly tell what your what all of your logs in one chunks are ordered. You can utilize it in numerous ways, and which is really helpful. So aggregation buffer looks like that. You have a block. For each block, you have application or like multiple applications, a lot of different applications. And for each application, you might have several different log levels. Another several facts about the aggregation buffers you need to know is buffer has maximal size, because if you will have too many log levels or like to have too many applications, otherwise you will just go with out of memory problem. So to not have this problem, we limited the size of the buffer. And basically, if your buffer after adding a new log entry will grow too big, we are going to flush the biggest aggregation to disk. Also, all data for specific block is being flushed to disk when we need to promote the block. Now, let's go to on-disk part, because we finished with everything in memory. And let's now talk about how do we flush our data on disk. I mentioned the chunks being written on disk multiple times. And now let's talk about its format. First of all, chunk has two different components. It has the data, like actual messages, actual entries, and it has the metadata. Metadata has a lot of different things. And first of all, it's obviously the minimum maximum timestamp. So you would understand which exactly logs you need, like which exactly chunks you need to read. If you are looking from, let's say, 1 p.m. to 5 p.m., you can kick out all the chunks which are outside of this time. After that, you have offsets of three different important things called Bloom filter metadata, like actual data offsets, and serious timestamp meta offsets. So what are these offsets? Offset is basically the actual physical location of this data where it was written. So when I write this data on disk, I get the position where I started to write it on disk and how many bytes did it require to write it on disk. And we have also some auxiliary stuff like scene series and scene keys. Scene series means without going into data of specific chunk, you can know which series you already have. So you would just like before querying, before actually doing any kind of additional I/O for reading these messages, you will just read the series and we'll check if you're like, will you be able to find what you're looking for inside of this chunk or not? And it goes both for series and for unindexed keys. Basically, all of this metadata is supposed to reduce the number of actual physical reads from disk as much as possible. So more metadata you have, less stuff you need to read. And this comes in both ways. So you need to balance on how many things in metadata you have. If you have too much metadata, it means your stuff will be like, your metadata will be it will be too hard to store it in memory, basically. Okay, too much information. Let's just say what messages is something written on disk. And these things, we are adding to the write-ahead log of chunks. Basically, we are writing it to disk, but we are not kicking them out from memory. We are leaving it there because we need it for querying. This is how our data format looks on disk. I will just tell what we are not using any kind of existing like any kind of existing formats like avro, thrift, or the protobuf, just because we decided what these formats are like pretty generic, and we need something which will have as little overhead as possible. And we know what our schema for data for actual messages are not changing very often. In fact, we didn't change it in last year. So we decided to write our own format, and it works pretty well for sequential reads. Also, we didn't just write it on disk because like logs are excessive and they can be compressed very well. So we decided to apply LZ4 compression to the top. And now you have probably the question, why do we have LZ4 compression, although we have much more efficient compressions, for example, ZSTD and like perhaps even Snappy? So this is the answer why. ZSTD is indeed much more efficient for the in case of compression. So compression means if you have the data, for example, 100 megabytes, compress should be somewhere like 50, for example, megabytes. And as you see on the right graph, ZSTD is instead about 12 or 15% more efficient, like the data after ZSTD is about 12% less than after LZ4. But if you will also check the second graph, decompressing logs is much more efficient and much faster with LZ4. That's why we decided what we will bite the bullet and take the network overhead which we need to have to transfer these logs for the reading node. But next time when it will be cached on disk, we will read it much faster when it would be with ZSTD. So your call data will have a like pretty bad access time, but when it is cached, it will be much better when it is with ZSTD. So yeah, basically you just write this Bloom filters series. And Bloom filters, which I didn't cover. Bloom filters is just a basic data structure which can tell you exactly something exists in a data set or not. If it says it exists in the data set, it means it can be false positive. But if it tells you it doesn't exist in a data set, it definitely doesn't exist in a data set. You don't need to go there. That's additional type of metadata which we have. So data blocks is just the stripes. It can be represented on disk as a stripes. And we are just appending our chunk, which is serialized, appending one after another, many more chunks. And each stripe has the size in our configuration. It can be configured up to 1 gigabyte. When this size is exceeded, we are creating more blocks. So why are we doing it? Basically, we want to be as nice to our S3 storage as possible. So we don't want to have a lot of files on our storage. So we decided to organize the block storage on top of block storage. And when it will be in block storage, we will if you have a big file and you want only chunk 2, you can, and if you know the offset of data for chunk 2, you can tell exactly, hey, give me the data from chunk 2, starting from offset A, and give me the number of bytes B. This way, you will get your data from one offset to another offset. And this is how it effectively looks like. You have just a lot of different threads building the stripes. After the stripe is finished, you start in the build another stripe. Okay, now let's talk about querying. Basically, the querying means like you store the data. It's very well, like all good, but nobody cares if you're storing the data if you don't allow to query it, right? So for querying, we are using Grafana Loki LogQL as well, because we find its possibilities of post-processing as very nice. And you also don't have, for example, in Lucene, we had a problem, but you can do a lot of things in multiple ways. And it's really confusing the users. And sometimes if you are doing if you are doing something, there is a chance you want something, but you're not getting something what you want. With Log Kestrel, with Loki, LogQL, it either works, either doesn't. So it's pretty simple, and we like it in that case. Okay, so for querying the logs, imagine you have like 4 blocks, and you have a query starting from 12 to 2 p.m. So first thing which you need to do, you need to identify the number of blocks which you have, which are like intersecting with this time range. After you found the number of blocks which are intersecting with this time range, you find all chunks which are applicable for these blocks. After that, you need to intern your query. Interning the query means you find the series applicable to the query from index. So you query the index and you say, hey, like give me all series for each of these blocks, which I can find the data for my query. And it gives you, like, for example, a set of series 1, 2, 3, 4, 5, 6. After it, you filtering out the chunks which are under these blocks, which have series 1, 2, 3, 4, 5, 6. So you're reducing the number of blocks which you need to read. Super nice. You're reducing the number of IO, less IO, everybody's happy. After you reduce the number of chunks by intersecting it with the series, you're filtering chunks intersecting with the time period. So meaning you can have chunk which is, for example, your query is starting from 12:30 to 1:30, but your chunk is starts from 12:05 and to 12:15. So you will reduce this number of chunks even more. After that, you will apply some additional optimization from the metadata, which I just talked about. You filter it by scene tags and Bloom filters. You just check if Bloom filter exists and if Bloom filter has the data which user requested. After you reduce it as well, you basically have like a least number of chunks possible, which is definitely having the data for your query. After you have this number of after you have these chunks, you need to implement, like you actually need to read the logs, no way around it. You need to read the logs and execute your query. After you executed your query on each of the chunk, you aggregate it to the level of blocks. For example, you had the 5 chunks here or 4 chunks on the left. You aggregate them together and have a result for the block. After it, you have a result per block. You aggregate results per block together. Basically, it's an absolute basic MapReduce, and this is how our querying works. Now let's talk about the types of queries in LogQL. First of all, you have histogram queries, meaning when you want to get the counts of some data occurrences. For example, you want to get the number of errors for last 5 hours. And when you have actually the log queries where you need to get the text and you need to get the whole data. Log queries, what we can say about it? First of all, result is text. This means what you will fetch a lot of data, even up to hundreds of megabytes sometimes if you have a big logs. Another important fact, user never wants to have a lot of logs. You don't want to read the whole database. And basically, user will just walk away and close the browser and will tell how bad your system is. So you just need to give them 1,000 of lines of logs, usually, or less or more, like 10,000, 100. But it always is limited to number, which is applicable to the query. After that, you don't need to process the all blocks, meaning if I'm querying the logs, which you have a lot of for last year, you don't need to iterate over the whole data for last year. You just need to check the data which you have like for the last 5 minutes, and you will probably get this 100 lines of log and you will return it back. And that's why the querying of logs is sequential on block level. So you're not going to query the logs from next block if you didn't finish the querying for one block. So if you're querying for last year, I will first query now minus 1 hour, then now minus 2 hours, and now minus 3 hours. Now, about histogram queries. Result is a time series. Basically, it just means what you have very small results. It will be almost always in kilobytes unless you have a lot of series. But it means that you need to process all the data. If you query the counts for last year, it means you need to calculate the data for last year, no way around it. And the volume of data can be obviously enormous. That's why we parallelize it as hard as possible. Like you have the 1 year of data, you run it on many executors, many threads, just make it finished as fast as possible. Okay, now let's talk about how do you actually scale the real time. Let's talk about, let's play a small game of system design. You have a small, you have an instance of real time. You can have a instance of real time. After it, you know what it needs to be queried by Federated API, and it needs to ingest the data from Kafka. What's the problem here? Obviously, you have a downtime during the deployment. When you do the okay, guys, sorry, there are a lot of questions. I will go through them at the end. Just bear with me for 10 more minutes. Basically, if you have just one node, you will have definitely the downtime during the deployment. So you definitely cannot just obviously have one single real-time node. So what you obviously do, you will just plug in another instance. You will have the primary and the backup. So what is good and bad about it? Primary and backup consume the same traffic under different consumer groups in Kafka. Consumer group in Kafka is just a mechanism how you can have exactly the same data for consumed multiple times. And the traffic fall back to backup in case the primary is unavailable. Okay, we solved it. So now you can just you can redeploy your application. Congrats. What's wrong with this here? Yeah, it's not scalable. We are talking about hundreds of terabytes of data per day. You definitely cannot process it on one node. So what can we do here? Yeah, we just split the whole stream into shards, and each shard will have primary and backup. Each shard will consume the same, each shard will consume some partitions, and all shards together will consume the whole volume of data from Kafka. Artists in the same shards are consuming the same topics and partitions, and Federated API will query all shards to serve the request. So now we can redeploy, now we can maintain the volume, and everybody is happy. Well, no, not really. You have a hardware duplication. It is impossible to scale. It is impossible to scale querying separately from ingestion. And in case you're being deployed on pods and or VMs, VM disk size is limited. So if you have so much data for last day, let's say you have more than us, and you have a petabyte of data per day, you will be in a world of trouble with this approach because you just will need so much VMs to store your data for last day. But it is so bad, but it is something we are working with right now, and it is how it is deployed in production, and it is some area of improvement for the future for us. Now, let's talk about historical. Historical is just a service which serves the queries for data which is older than 24 hours. We'll quickly go through that. Not so important. I mean, the data and data flow, the MapReduce, the querying flow is exactly the same in real time. Only thing matters is how you query the data, how do you provide the interfaces implementation to the historical. Basically, first thing you do, you get the blocks, metadata meaning how many blocks and partitions did you have for for your time period of your query. After you got this, you definitely cache it because you don't want to call to Postgres for your queries, for all of them. You cache it on memory. After you obtain the blocks rows, you get the metadata for them, you get the internals and everything. After you got this, you get the metadata of chunks, and you cache all of this in memory. After you identified which chunks you need to read, you fetch the logs from chunks, and going to chunks as I said, going for data from Ceph every time. As I said, it's not the best idea, so we decided to cache it on disk as well, historical. And we have many more caches. We have block level response cache, and we have chunk level response cache, and we have some more caches, which I'm not going to talk today. And the morale here is, if you have a network related service or the data reading node, just cache as much as you can, and it will make you be happy, and it will help you to survive the workload. Caching is the king. This is the morale. Okay, and the last component, bear with me, guys, 5-6 more minutes, please. Federated API. Federated API is the component which distributes the queries between real-time and historical, and also it executes the cross-DC requests. So why do we need cross-DC? Basically, we don't have any kind of cross-DC replication because it will be, first of all, it's obviously too hard and we don't want to do that, but it's not really the actual reason. If you're going to replicate all the logs, you will burn the network. Everybody will not be happy. So we query logs cross-DC only in case we are required. Meaning, if you need to get the data from all 4 or 10 data centers, you need to go and distribute this query to all other data centers. Now let's talk about local query processing. So imagine you have a query for last 4 days. When you have a query for last 4 days, you obviously go to cross DC, which I just discussed. But in local DC, you do service discovery call because you have a lot of different services. After you identified the services which you need to go, you query the RT cluster for last day, meaning you query all RTs which we discussed just now. After it, using the service discovery, you identify how many historicals you have, and you split this request. Basically, last day goes to real time, and the rest of the data, the rest of the time range goes to historicals. And here is the spiciest decision we made. Basically, for each of the requests, we are querying all historicals. And for each request, we are adding the ID of specific instance. So for example, you have servers A, B, C. So you sort them. A gets ID 1 and C gets ID 3. And also you send the total number of instances free. What next? So you send query to each historical. Each historical receives instance ID and total number of servers. For each chunk, you remember this MapReduce histogram, right? Like MapReduce picture. When you identify the chunk, there is additional, when you figure out, do you need the read chunk or not? On each historical, you calculate the hash of the chunk metadata, and you decide which chunk, like which instance out of the ring. You have total number of instances, right? In the current instance, you identify, does this instance ID, like does the current instance which I have ID for is actually the owner of this chunk? If like if it is the owner of this chunk for this hash ring which I have. So like imagine you have like the same thing in the same way as Cassandra does the instance selection using consistent hashing, but we are doing it a bit in a weird structure. So and we are also using rendezvous hashing, not consistent hashing, because not going to dive into details because we don't have time. The rendezvous hashing is better if you have small number of instances, and if you need better like even spreading of the workload. So using this determination, each historical will read only its part of the chunks, and you will get the whole data. Like for example, you have 25 chunks, 5 instances, and each chunk is going to read each historical will read exactly 5 chunks. So you aggregate this data in each historical, you get it back to Federated API, and using this formula, Federated API will have the data for the all historical time range. What's the problem with this approach? Let's start with the good part. So quite straightforward. It gives you the best possible cache hit rate, and each instance receives even workload. And Federated API doesn't know anything about the metadata as well, like super simple. That's exactly the reason why we did pick it up. But the bad side is querying all instances for each request. Like, for example, if you have 10 instances, you need to query 10 instances. If you have 100 instances, you will need to query 100 instances. Another problem is all historicals need to cache the metadata. That's something really big, and this is really problematic. So, for example, if your metadata will grow too big, you will need to vertically scale each historical, because horizontal scaling will not help. Okay. Thank you for bearing with me to the end. Here comes the summary. The strong sides of the system: real-time logs access, because the data stored on the same ingesting nodes as they being queried. The access is super fast, no network is required. Indexing, we have additional scaling as well as the low cardinality indexes and unlimited cardinality indexes. Scalability, we can scale pretty well. Also efficient resource utilization. Since this whole thing is written in Rust, we are quite resource efficient, and we don't need to worry about things like boxing and garbage collection and other things from Java. And the data compression. Since we are using dictionaries, since we are using compression, we are using serieses, we are quite resource efficient, and data compression is pretty good. Something we need to improve: real-time and ingestion. Basically, all the lists from the backlog we need to improve to the real-time. Another problem is in historical, logs must be downloaded from S3 before they can be processed. Not so much you can do about it, but currently, if you group by specific field, or if you're interested only in one field during the histogram aggregation, you will still need to read the whole message. And it means you will load much more data than you actually need to serve your query. And this is something we are going to mitigate in the sooner future by onboarding to Parquet format. All right, that's it from my side. Please submit your feedback, and Nan, let's start with the Q&A session.
Okay, thank you, Eugene. Great sharing. So now we open for questions. Eugene, you want to start from the questions in the chat first? So we have questions from Eugene as well.
Yes, thank you, Nan. I see the question. Regarding the compression speed measurements, are those numbers for just one CPU? Yes, these numbers are just for one CPU. Basically, I mean, you have a lot of different threads and workers going on, and it means like, yeah, but they will have the same problems, or the same pros and cons basically for each algorithm. Can we have both histograms and logs query both added to some dashboard? Yes, you definitely can, and it will be just a separate queries to the system, but you can definitely do it. On the user side, you can do it. How does the reverse ordering sorting works? Won't you need to read all blocks to the end? Yes and no. It's actually the great question. I really like it. So for the sorting of blocks, we will just start, like, for example, you query the data for last year. We will find the last block which you need, and we will basically have a queue, like basically the heap, you can say. We will read the heap, and we will identify the last logs in each block. And that's how we are going to do it. But order of blocks will be absolutely different if you will fetch the sorting from the start. So basically this is how it works, but it's definitely less efficient than getting the first logs. Since data compression requires a lot of CPU work, using multi-cores helps to improve the compression speed. Yeah, I mean, we definitely can explore more algorithms, I guess, but we didn't explore the internals of others compression algorithms, and I think we are currently deployed. I mean, I think currently we're all use only single thread for compression. So why not use Loki? Other things what Loki can do. So yeah, that's also the great question. So first of all, I want to stress out what the Grafana Loki is a great tool, but it had some limitations because of which we couldn't use it in Agoda. First of all, for example, in Loki, we couldn't have the custom indexing on trace IDs. So in Loki, if you would need to query by some trace ID for, let's say, 6 months of data, you would need to read the whole 6 months of data. In our case, you just need to, you can just use Bloom filters. And in that case, you will need to just read Bloom filters. And we are actually currently working on additional levels of indexing. So because we are owners on our system, we can customize our indexing as much as possible. That was the core idea behind writing our own system. It's just like it utilizes the same locale. It utilizes more or less the same principles, but it requires a bit different workload. Okay, guys, any other questions?
Any other questions? You can unmute yourself as well. All right. If not, then we will end the session here. Thank you so much, Eugene, for the great presentation today. And thank you everyone for tuning in. Hope you have learned something useful. Before you go, I have some news for Agodans. So yeah, we just create this group on GitLab called Tech Culture, where everyone can suggest tech talk topics in the future and upvote for topics that excite you the most. So we can work together to schedule the talks. Yeah, so please do visit the group and explore it, or reach out to me if you have any questions. We will also have another initiative coming up this month, so please stay tuned for the announcement. So that's a wrap for today. Thank you everyone for attending. Don't forget to provide feedback as well. Have a good rest of the week.
Thank you so much,
Bye.
guys, for
Thank you.
listening.